then that's easy to plot out. But you should be able to just draw energy versus 1, 2, 3, 4 electrons, right? And this goes up and then shoots up for number 4. So you don't even need to know the values of the ionization energy. You just need to know that it increases a little bit for the outer shell electrons and then shoots up. And so if I tell you that there's a strong absorbance for zinc oxide at 1500 in the FTIR, you don't need to know anything about what else is happening. You just need to draw a strong absorbance right there. Yeah?
Why is it centimeters to the -1?
Oh, okay. That's a good question. So what kind of number is this? What does centimeters to the -1 mean? Frequency? Frequency, yeah, frequency. So this is 1500 cycles per centimeter. What's the normal units of frequency?
Hertz.
Hertz, right? So why can we do cycles per second or cycles per centimeter? They mean the same thing for electromagnetic radiation, right? Because wavelength, frequency, and the speed of light are all wrapped up into one number for radiation. So if we specify a frequency, we automatically know what the wavelength is, right? Does everyone not get that? What is it? Wavelength equals frequency over speed of light? Is that how it works? Yeah. So whether we specify wavelength in nanometers or we specify frequency, doesn't matter, right? We can calculate one from the other. So on spectroscopy, the most important thing is if I tell you like just simple adsorption, you know, where are the adsorptions? Draw a transmission spectrum, something absorbs this. That's the most important part of the spectroscopy part.
So
There were other, yeah.
Is there another way? Speed
Oh.
light?
Yeah.
H.
Oh, I'm confused now.
C over L.
C over
Yes.
L.
HC over L. HC over L.
Is that better? Okay. Yeah.
What is the dielectric constant?
Yeah. So dielectric constant is related to the dielectric permittivity. So is related to just make sure my camera is still recording here. Oh, looks good. Okay. So the dielectric constant is related to the dielectric permittivity. What does the dielectric permittivity describe? How polarizable our medium is, right? So dielectric permittivity is related to polarizability. So you know about the polarizability of molecules, right? You know about the polarizability of bromine gas versus fluorine gas. What's more polarizable? Bromine, right? It's got more electrons, more polarizable. So the definition of the dielectric constant is the dielectric permittivity over the dielectric permittivity of vacuum. That's not a very useful equation for you to know. However, you need to know that dielectric constant is related to the dielectric permittivity. And from that, you can relate that to the polarizability, etc., etc. So what has a higher dielectric constant? Bromine or fluorine? Bromine, right? Bromine has a higher dielectric permittivity. It's more polarizable, therefore it has a higher dielectric constant. How is the dielectric constant related to the refractive index? It's K equals N squared, right? Minus some loss terms or some small. Yeah?
Is there like a definition for refractive index? Because like I know the relationship, but what is refractive index?
Yeah, so refractive index is the ability of the material to respond to an oscillating electric field.
Is it kind of the same thing as dielectric permittivity?
Yeah, exactly the same. They're all related to one another. So if dielectric constant is a refractive index squared, if one increases, the other increases. If one goes down, the other goes down. If dielectric permittivity goes up, dielectric constant goes up, refractive index goes up. So they're all related to one another. So when you ask what is dielectric constant, I would say that the dielectric constant describes the ability of the material to respond to an electric field. So if I tell you that material 1 has a high response and material 2 has a low response, which one has a higher dielectric constant? Material 1. High response is high dielectric constant. Does that work on defining what the dielectric constant is?
Yeah. Do we just have to know that they're related to each other, not actually like solving long, complicated problems?
You're not going to have to solve have you had to solve long, complicated problems in the homework?
No.
No, yeah. So you've had to solve some little math problems, right? Van der Waals forces, really simple stuff. If you have to do any math on the exam, it's going to be little simple stuff. But I'm after ideas, right? If you tell me that fluorine has a higher dielectric constant than bromine, it doesn't matter what calculations you can do. You don't understand the concept of how they're related with polarizability. So I'm going to be going after concepts just like the homework. Yeah.
So if you polarize something that's putting an electric field on the substance, is that the dielectric constant, or will that hold the same? Or would you need a stronger electric field if the dielectric constant is higher or lower than something else?
Yeah, so when you polarize something, you're not changing its dielectric constant. Its dielectric constant is what it is. But what do we know about frequency and dielectric constant?
There's inversely related.
Yeah, why is that? So on most everyone's homework, I wrote down frequency and N, right? And it goes kind of like this. Why is that? Does anyone know why? So if I shake something at low frequency, can it respond to that? Versus if I shake something really fast at high frequency, can it respond to that?
Yes.
It has more energy.
Well, it's got more energy,
So
but
you're going to respond more if you got more energy.
well, you think about Jell-O, right? Shake Jell-O slowly. The whole Jell-O's moving. It's really responding. You shake Jell-O quickly, and it's just jiggling a little bit, right? So its dielectric constant is low. That's a very bad analogy. But what it really comes down to is how fast can those electrons respond, right? If I put a really high frequency into nitrogen, those electrons have their own frequency. They're zipping around there, right? So if I put a really high frequency in there, those electrons might not be able to respond at this high frequency. Electrons move at maybe 10 to the 15 per second, 10 to the 15 orbits per second, something like that. If I put 10 to the 20 in here, the electrons aren't going to be able to move that fast. But if I put 10 to the 1 in here, I can shake those electrons all around. And so the dielectric constant will rise up at lower frequency. You have more time for the material to respond. Yeah?
So is that from wave patterns, constructive and destructive waves, or if the material's in phase or out of phase, or not really?
No, it just has to do with what's responding in the material at a given frequency. So at low frequency, you can move more stuff around in the molecules. You can have reorientation of dipoles, right? So if I have water, well, water's a good one. So if I put 10 to the 1 frequency in here, I can move that whole water molecule. I can move that dipole so that thing has a high response and its refractive index or dielectric constant will be high. Remember, it's the same thing whether I'm talking dielectric permittivity, dielectric constant, or refractive index. All three of them have the same plot. So if I put a low frequency in here, I get dipoles to rotate, I get all that high response of that material. If I put a high frequency in here, maybe I get some electron response, but I don't get any dipole reorientation, and so the dielectric constant will decrease as I increase the frequency. So it really has to do with how fast the molecule can respond to my oscillating electric field. Yeah?
Just make sure I understand this. So if you have substance X and it responds at a low frequency, that means it'll have a high refractive index, which means it also has a high dielectric constant.
Yeah.
Okay, and then that curve isn't for just one substance, it's for refractive indexes that could vary with different substances.
Yeah. So each substance, will have
Like balsam.
a different curve, right? So this is material 1, this is material 2, this is material 3, right? The general shape of the curve is like this, right? When we heat up every gas, we know that the pressure will increase. That's the general trend, right? But we know the pressure will increase differently for different gases. Same with refractive index. Each material will have its own separate curve, but they're all decreasing as a function of frequency.
Okay, and then the humps in the curve, they just represent frequencies that material responding more to.
Yeah, exactly. So they correspond, if you look in the notes, they correspond to